All right, let's get started here. It's my great pleasure to introduce my colleague and fellow floor mate on the fifth floor, Dr. Jianjun Yin, to give today's colloquium. Jianjun requested to me, actually, he said, keep it short, please. So I'll try my best to do that, but Jianjun is a very accomplished scientist, but I'm going to try and summarize his introduction here. So Jianjun started off with a bachelor's at the Nanjing Institute of Meteorology, and then went on to do a master's at the Chinese Academy of Meteorological Sciences. And then after that, he went and he started his PhD at the University of Illinois at Urbana-Champaign, where he worked with actually Mike Schlesinger. He then went on to go do a postdoc at GFDL, one of the premier institutes for climate modeling in the United States. And he worked at, so GFDL is the Geophysical Fluid Dynamics Laboratory, for those of you who may not be familiar. And then he spent some time in Florida as a scientist at the Florida State University. And then, so Joellen says that it's the premier modeling center in the world. So I will correct myself. Thank you, Joellen. And then after that, Jianjun joined us here in 2011, I believe. And so Jianjun touches upon several different aspects of climate dynamics, his work and his research group. And in particular, as this talk, he's going to share some results that are related to sea level rise along the US Atlantic coast. And he's published several papers in prestigious journals like Nature Geoscience and so on, but also several articles in Geophysical Research Letters and Journal of Climate, and et cetera. And I just want to mention that a couple of weeks ago, I was in a sort of a summit organized by the Prime Minister's Office of India. And there were all these big climate modelers. Don't ask me what I was doing there. But it's a mark of Jianjun's work that his work relating impacts of sea level rise was heavily featured in this meeting. And there were a lot of people like V. Ramaswamy and Atul Jain who really praised some of the recent work coming out from Jianjun's lab. So without further ado, I kept it to 2 minutes, Jianjun, so hopefully that's okay for you. Take it away with today's colloquium. Thank you for giving a talk. And as always, I'm going to moderate questions later on, so please feel free to enter questions into the chat, or you may raise your hand at the end of the talk, and then I can moderate those questions. So take it away, Jianjun.
Thank you, Carl. And today I'm going to talk about sea level rise and storm surge. So for people living in Arizona, so this may not be a problem if you don't have a vacation house at the beach. But this is a big problem for the Atlantic coastal community. So I will show you in my talk. So my talk is based on this paper published early this year. So if you want to find some details, so you can take a look at this paper. And also this work is a collaboration with GFDL and colleagues over there. So I will start with some background information and talk about the global sea level rise and regional sea level rise, storm and storm surge. And then I will show you GFDL CN4 model simulations of storm-related extreme sea level along the US Atlantic coast. So here, Atlantic coast includes both East Coast and the Gulf of Mexico coast. So the impact of climate change and the sea level rise on the extreme sea level events will be discussed in section 3 and followed by the conclusions. So global sea level rise is the gradual, persistent, and long-term trend of sea level. So there are two major factors that contribute to global sea level rise. The first factor is thermal expansion. So if you consider this column is the ocean, global ocean. So when the ocean gets warmer, thermal expansion can cause sea level rise. So this is the first factor. So the second factor is the melting of land ice. So especially melting of the polar ice sheet, Greenland ice sheet, and the Antarctic ice sheet. So the meltwater flows into the ocean and increase the total mass of the ocean, therefore raise the global sea level. So this is the second factor. So the thermal expansion is also called global steric sea level rise. And so this is the second factor is the mass component. So the left panel shows the instrumental records of global mean surface temperature from 5 data sets. So you can see the general upward warming trend since 1850. So in response to this warming climate, so the global sea level is rising. So the right panel shows the satellite observed global mean sea level. So the linear trend of global sea level is 3.3 millimeter per year since 1993. But the biggest concern is not the rise rate. Actually, it's the acceleration here. So you can see if you fit a curve, so you can see the acceleration even during this short time period. So the sea level response to warming climate can take a long time. So it's not easy to stop it if it's accelerating. So to study the coastal impact of sea level rise, we need to know the regional sea level rise information. So regional sea level rise is more complex with additional factors involved. So for example, ocean dynamics, air-sea interaction, geo-age change, so land vertical motion. So in this talk, I will focus on the ocean dynamics and the air-sea interaction. So the geo-age change is related to the ice sheet melt, the Greenland ice sheet and Antarctic ice sheet melt. So that can redistribute the mass in the Earth system, therefore can modify the geo-age, therefore can cause the regional sea level rise. And the land vertical motion, so the most of the Atlantic coastal region of the US is influenced by subsidence, land subsidence. So some subsidence is due to the glacial isostatic adjustment, which is paleoclimate related. And some other subsidence is climate unrelated. But due to human activities, so such as the water oil extraction especially along the Texas coast, and also the constructions of dams, buildings. So actually that can depress the land surface, therefore can cause the relative sea level rise. So this diagram, schematic diagram, summarizes all the factors that influence the global sea level and the regional sea level. So climate models are designed to simulate the geophysical fluid component. So like the ocean, like the atmosphere, climate, but the process climate model do not simulate the processes related to the solid Earth. In particular, most climate models do not have an ice sheet component. The Antarctic ice sheet and the Greenland ice sheet are not included in climate model at this point. So therefore, climate model cannot simulate the land ice melt, that part. So this is something I want to emphasize at the beginning. So in my talk, so land ice melt is not included. We only study the ocean atmosphere processes. So at the coastal region, so extreme sea level events can occur. So these events are often related to extreme severe storms and storm surge. So storms or cyclones can be tropical cyclone, TC. So you know that a hurricane is strong tropical cyclone. And this is the typical structure of hurricane. So you can see the convection. So the energy comes from the huge convection and also the latent heat release inside of the hurricane. And also it requires very warm ocean temperature. So cyclones can be extratropical, so like the nor'easters along the east coast of US. So this is the typical structure of nor'easters, extratropical cyclone. So you see the energy comes from the potential energy release. So like associated with cold air, cold temperature on this side and warm temperature on that side. So extratropical cyclone critically depends on the temperature gradient, the so-called baroclinicity. So all these synoptic systems are generated from chaotic process in the atmosphere. And also they are also influenced by ENSO, by climate modes like ENSO, El Nino Southern Oscillation, the North Atlantic Oscillation, NAO, the Atlantic Multi-Decadal Variability, AMV, as well as the aerosol and greenhouse gas forcing. So for example, we know the El Nino can suppress the hurricane over the Atlantic Ocean basin. And therefore, it really requires a fully coupled weather climate modeling system to study storm and storm surge. So severe storm can cause storm surge. Storm surge is the strong and transient sea level increase at the local scale. So the storm surge is the biggest killer associated with hurricane. So it is responsible for more than half of the fatalities during hurricane. And also it can cause coastal flooding, beach erosion, and socio-economic damages. So the storm surge height critically depends on storm characteristics. So strong storms, large size, and perpendicular landfall, so can cause higher storm surge. So storm surge also influenced by coastal geometry and bathymetry. So for example, if the continental shelf is shallow and is broad, so the storm surge is higher. And also peak surge often occur during high tides. So there's a nonlinear tide surge interaction. So most climate models do not simulate tides. So therefore, this tide surge interaction is not included in my talk. So this is another caveat. So this is the hurricane season this year. We know that we just experienced a very busy hurricane season. So 27 storms over the Atlantic Ocean, North Atlantic, and 10 of them made landfall. So another hurricane, just yesterday, another hurricane made landfall at New Orleans. So this is a satellite image of Hurricane Laura 2 months ago. So Laura was a Cat 4 hurricane at landfall. So Laura caused extreme surge event along the Louisiana coast. So the storm surge from Laura was up to 15 feet. So this is the storm surge recorded by one tide gauge. So this is a tide gauge along the Louisiana coast. So you can see it is tall, right? So therefore, this device was designed for to measure the extreme surge event, not just measure the tide. Actually, it's the surge gauge. So this is the recorded water level at this location. So the blue curve is the predicted tides, and the green curve is the measured water level. So the difference between blue curve and the green curve is the storm surge height. So you can see at this location during Hurricane Laura, so the storm surge was up to 10 feet. So this extreme surge event actually caused catastrophic coastal flooding. So you see the picture here along the Louisiana coast. Okay, not only hurricane, but also extratropical cyclone can cause coastal flooding, extreme surge event. So some of you still remember this bomb cyclone a few years ago. So this actually this winter snowstorm actually froze the entire northeastern U.S. So extreme cold weather, and also the wind it was very strong, hurricane force wind. So this winter storm actually caused the winter coastal flooding. So like this at Boston, so you can see the ice and the water on road. So this is a winter coastal flooding. And also, you know, the Sandy. Sandy is a hybrid tropical extratropical storm system, right? So, and also it caused catastrophic impact like along the New Jersey coast. So you know, you see that all different kinds of systems can cause a surge event and coastal flooding. Okay, next let's look at the GFDL CM4 global climate model simulations of extreme sea level events. So GFDL CM4 is the latest generation of global climate models developed and used at the Geophysical Fluid Dynamics Laboratory, GFDL, of NOAA. So here I just give you a very brief description of the model. So, but you can find details of the model in this documentation paper. So CM4 has been used for the recent CMIP6 project. So this is a climate modeling community effort. So the atmospheric component model has a 1 degree resolution, 33 vertical levels, and uses updated model physics. And the oceanic component model is based on MOM6. There are 75 hybrid vertical layers, and also the horizontal resolution is eddy permitting quarter-degree horizontal resolution. So that means at the mid-latitude, there is a grid point every 20 kilometers. So, and compared with the previous climate model generation, so this resolution is relatively high resolution. And also another higher resolution version has been configured. So this is a CM4 high-res HR. So in CM4 high-res, so the atmospheric model resolution is refined to half degree, 0.5 degree. So I will show you this. The model resolution is critical in simulating the hurricane simulation. Okay, so under the CMIP6 protocol, a series of climate change experiments have been performed with CM4. So this table lists all the climate change experiments. So in this talk, I will focus on the two simulations. One is the PI control, the control simulation of CM4. So in this simulation, the radiative forcing is kept at 1850 level. So that means the simulation is without climate change. So this is a control simulation. And also the duration of this simulation is 150 year. And the other simulation is the so-called 1% CO2 simulation. So in this simulation, so the atmospheric CO2 concentration increases by 1% per year. 1% per year over this 150-year period. So this simulation is branched from the control simulation. So by comparing by comparing these two simulations, we can see the impact of climate change and sea level rise on the extreme sea level events. So there are also other simulations like a historical simulation, projection, 21st century projection under different emission scenarios. So the results for these experiments are quantitatively similar to the 1% CO2 simulation. And the magnitude of the change increases with the increase of the external forcing. So I just used the 1% CO2 to show the impact here. And also there are a couple of experiments with the CM4 high res, that version. I will briefly show the simulation results. Okay, so this is the coastal geometry and the bathymetry. So the left panel shows the Atlantic coastline in nature, as highlighted by the red color. So the stars are the big coastal cities. So this is Boston, this is New York City, so this is Charleston, Miami, New Orleans, and Houston. And the right panel shows is the representation of in CM4. So you see the CM4 roughly resolves important bays, like the Chesapeake Bay right here, and also their connections to the open ocean. But CM4, the resolution is not fine enough to resolve smaller features. So like the Barrier Island east of North Carolina, south of Florida, and also along the Texas coast. So according to the correlation of coastal sea level, we divide the Atlantic coast into 3 regions: the northeast coast, the southeast coast, and the Gulf of Mexico coast. So this is a tropical and extratropical cyclone simulation in CM4, the control run. So the left panels are the global map of the storm track for TC, tropical cyclone, and for EC, extratropical cyclone. So the right panels is the storm track over Atlantic Ocean basin. So you see the CM4 can better simulate a strong TC and EC with hurricane force wind, realistic storm track, and also reasonable seasonal cycle and intra-annual variability. So maybe in CM4, the 1 degree resolution, the low relatively the standard version of CM4. So we can see Cat 1 hurricane. So in the CM4 high res, we can see Cat 3 hurricane, but both versions do not simulate the strongest hurricane. Cat 4, Cat 5 hurricane are not simulated in both versions. And also the contour in B is the subtropical high, so that can steer the TC, and the contour in D is the surface temperature gradient. So usually the EC actually follow the frontal region, the surface front. Okay, so this is the mean dynamic sea level observed by satellite. So for this 20-year period, so dynamic sea level by definition is a departure of sea surface height from the geoid. So this geoid is the equipotential surface. So if the ocean is at rest or there's no ocean current, so the ocean surface should coincide with the geoid. So this deviation is due to ocean circulation, ocean current. And you see the ocean surface is not flat. There's the ocean topography, just like the land topography, but it's very small, only a few meters here. So if you plot the dynamic sea level along the 30-degree latitude, so you can see the sharp dynamic sea level gradient across the Gulf Stream. Right here, it's the Gulf Stream region. And right here, you can see the sea level gradient across the crucial. So this is required by the geostrophic balance. So this gradient, sea level gradient, actually drives the western boundary current, the Gulf Stream and the crucial. So in the next section, I will show you climate change is going to change the ocean circulation, and therefore can modify the cross-current sea level gradient. So that can cause extra sea level rise along the east coast of the US. So in the next section. So in climate model, so dynamic sea level is the departure of the global mean sea level. It's a regional departure from the global mean sea level. So therefore, by this definition, so dynamic sea level and the dynamic sea level anomaly always have a zero global mean. So it just shows the sea level rise pattern. Okay, now let's compare the simulation of CN4 for the dynamic sea level in the control. So the left three panels are the satellite observation, and the right three panels are the CN4 simulation. So the upper two panels are the long-term mean dynamic sea level. So you can see the similarity between the two panels. So CN4 does a nice job. The middle two panels are the seasonal cycle of dynamic sea level. So basically, this is the September minus March. So seasonal cycle. So you see the seasonal cycle can be up to 0.2 meter, especially along the Gulf Stream region and also along the crucial region in the North Pacific. So this seasonal cycle is due to the seasonal heating and cooling of the ocean surface of the ocean, and also due to the seasonal change of the prevailing wind and the ocean current in this region. And also you can see the similarity between these two panels. And the bottom two panels are the daily dynamic sea level variability. So daily data here is detrended and deseasonalized. So it's the anomaly, daily anomaly. So the high value is induced by the mesoscale eddy in the ocean. That's the weather in the ocean. And especially along the Gulf Stream region and also along the crucial, right? So CN4, as you can see, actually somewhat underestimates the mesoscale eddy activity in the control simulation. So this is partly due to the eddy permitting resolution, quarter degree eddy permitting, not eddy resolving resolution. Okay, to study the storm surge, we need to analyze the daily sea level anomaly. So ideally, we need to analyze the hourly sea level, because the peak surge occur hourly. However, it's still not possible to save the hourly data, especially for high resolution global climate model. So here we just use the daily sea level information from CM4. So the total surge, delta H, equals the sum of two parts, wind surge and pressure surge. So delta eta plus delta B. So this is a wind surge, this is a pressure surge. So if you think this is a hurricane, so the strong wind can push water onshore. So therefore, this surge is a wind surge. And at the center of the hurricane, so it's a low pressure region. So the low pressure suck the ocean surface upward, just like you use the straw to drink water, right? So this low pressure actually can cause the pressure surge. So the total surge, delta H, is the sum of wind surge and the pressure surge. So again, in all these terms, the daily climatology is removed. So we don't take the seasonal cycle into account. And so this is the control, storm surge in the control simulation. In the CO2 experiment, so the daily sea level anomaly for daily sea level anomaly, we need to take into account the regional dynamic sea level rise and the global steric sea level rise, and also the storm surge. So this is this schematic compares the control and the CO2 experiment. So in the control, you see there's only a storm surge, right? So the extreme sea level is caused only by the surge, And in the CO2 experiment, so because the ocean gets warmer, so it can cause global steric sea level rise. That's the thermal expansion part. And also the change of the ocean circulation can cause regional dynamic sea level rise. So that's the deviation from the global mean. So the total sea level rise is the sum of global steric sea level rise and the regional dynamic sea level rise. And also the storm surge is superimposed on the total sea level rise. So you see we needed to consider all these processes, all these factors for extreme sea level events. Okay, so this is a large surge event simulated by the CM4 model. So in panel A, so this is a wind surge. So the contour is the sea surface, sea level pressure anomaly. So basically you see the low pressure. This is a strong tropical cyclone in the Gulf of Mexico. So you see the shading is the wind surge. You can see this tropical cyclone caused an extreme surge event at New Orleans up to 1.8 meter. And so this is storm wind. So you see the onshore wind, very strong onshore wind caused this wind surge right here. And this green line is the storm track. So B is the pressure surge. Also, this is a storm, and also you see the pressure surge is smaller, much smaller. And so D is the storm precipitation. So you see the heavy rainfall can dump a lot of water to the ocean surface. Therefore, the heavy rainfall can increase the surge height. And E is the surface current. So you can see the loop current right here, and also the Gulf Stream east of Florida. So because this the resolution is relatively high, so the Gulf Stream is strong, it's a narrow and a very fast jet in the ocean. And when the tropical cyclone actually pass over the loop current, so you can see actually it intensifies very rapidly. So this line here, color line, show the intensity change during the propagation of the tropical cyclone. And F is the sea surface temperature anomaly. So you see the strong wind actually stirs the ocean. That can bring the cool water from the subsurface layer to the surface. And so therefore you can see the so-called cool wake just after this tropical cyclone. Okay, so this compares the tropical cyclone or hurricane simulation between the standard version of CM4 and also the high res, the CM4 high res. Remember, so this is a 1 degree atmosphere. So the high res has a ½ degree atmosphere. So you can see if you increase the atmospheric model resolution, so the tropical cyclone or hurricane becomes stronger. So the wind, storm wind becomes stronger. And the size of the hurricane becomes smaller. So if you compare, and also the storm precipitation becomes heavier. So therefore, the model resolution is quite important in the hurricane simulation. Because the actual tropical cyclone has a much larger size. So therefore, the actual tropical cyclone nor'easters simulations are similar between CM4 and CM4 high res. Okay, so this is some statistics of daily sea level anomaly in the control simulation of CM4. So the left panel shows the standard deviation of the daily sea level anomaly, also detrended and designalized. So you can see the contour line here. So that's the 100-meter isobath. So this 100-meter isobath actually separate the coastal ocean process from the ocean interior dynamics. So you see the separation, clear separation. So this is the standard deviation. The middle panel is the skewness of the daily sea level anomaly. So you see its positive value, positive skewness. So this is because so positive skewness means you have a longer tail, right? So the positive surge dominates over the negative surge. So if you go back to this plot, so this is the storm, right? So on the east side of the storm, so you can see the positive storm surge because the onshore wind is very strong. And on the west side of the storm, you can see it's offshore wind, right? So, but the offshore wind is much weaker. That's due to the land friction. So therefore, the positive surge dominates over the negative surge. So therefore, you get a positive skewness along the Atlantic coast of the US. And the kurtosis is more useful in terms of extreme sea level. So basically, kurtosis measure the tailedness, the tail, how long the tail is. So high value of kurtosis means more extreme surge event. So from this map, you can see the New Orleans. New Orleans is a hotspot for extreme storm surge because of the high kurtosis value here. And also high value of kurtosis can be found along the west coast of Florida here, and also along the south coast of Texas. So overall, so the Gulf Coast is more vulnerable in terms of storm surge and extreme sea level events. Okay, so we also evaluated the return levels of storm surge. So the left three panels are the observed daily sea level from tide gauge data. So also detrended and designalized. So daily data at New York City, Charleston, and Galveston. So the horizontal lines, the upper horizontal line is the return level for 1 in 100 year event. So in other words, so the surge can reach this level every 100 years. So the middle horizontal line is the 1 in 10 year event. The lower horizontal line is 1 in 1 year event. So this is the return levels from the tide gauge data. So the middle three panels are the CM4 simulations, and the right three panels are the CM4 high-res simulations. So you see the both versions underestimate the return levels at New York City. The return levels are better simulated at Charleston, and the return level at Galveston. So it's actually underestimated in the CM4 simulation, but overestimated in the CM4 high-res simulation. So that's because the hurricane is stronger in the CM4 high-res. So I won't go to the details of this evaluation. You can find some details in the paper. Okay, so wind and pressure surge in the control run. So this panel A plot the daily sea level at New Orleans over 1 year period. So you can see this spike during summer season, so induced by the landfalling hurricane. So this is the daily sea level at New York City also over 1 year period. And you can see the the sea level actually is more active during winter season, during cold season. So these spikes are induced by strong nor'easters, strong extratropical cyclone. So the right two panels plot the wind surge or pressure surge as function versus the total surge. So the horizontal is the total surge, vertical is the wind surge or pressure surge. So from this correlation regression, you see the wind surge by far dominates. So next, we especially at New Orleans, especially at this location. So this is a wind surge relationship. So A shows the typical wind pattern for the large surge event at New Orleans. So B shows the typical wind pattern for the large surge event at New York. And C shows C plot the wind surge height as a function of wind speed. So we just want to quantify the relationship. So you can see there's a quadratic relationship between wind surge height and the wind speed, especially at New Orleans. So the wind is more efficient at reaching coastal sea level along the coast, along the Gulf Coast. So therefore, the coastal vulnerability increases non-linearly as a storm increase the intensity. So this is for New Orleans and New York. So this D shows the other coastal cities, the relationship. Okay, so so far we have discussed the extreme sea level events in the control simulation. So next, let's look at the 1% CO2 simulation, the impact of climate change and sea level rise on the extreme sea level. So in response to 1% CO2, again, so the atmospheric CO2 concentration increases by 1% per year over a 150-year period. So in response to 1% CO2, so you can see the global surface air temperature and also global sea surface temperature increases, right? So this is a global warming trend. And also the warming ocean can causes the thermal expansion, right? So global steric sea level rise, maybe 0.37 meter over the 150-year period. So this is the global sea level rise. So the right panel shows that regional dynamic sea level rise due to the ocean circulation change. So at the coastal cities from Halifax to Houston. So you see the dynamic sea level rise is relatively larger along the East Coast, the solar lines. And the dynamic sea level rise is relatively small during the Gulf Coast, the dashed lines. So this is the pattern of the dynamic sea level change. So the contour is the mean dynamic sea level in the control run, and the shading, color shading, is the dynamic sea level anomaly during the last 20 years of the 1% CO2 experiment. So you can see the dynamic sea level rise along the east coast of the US, actually also the east coast of Canada. And also the gradient, the sea level gradient across the Gulf Stream actually declines. So this is the dynamic sea level anomaly. So this is the sea surface temperature anomaly. So you see the in this plot, so the global mean sea surface temperature anomaly is removed to better show the pattern, the regional pattern. So under the CO2 forcing, so you can see the ocean warming is faster north of the Gulf Stream in this region. And the ocean warming is slower in the subpolar gyre region, in this region. And also there's another fast warming region in the Nordic Sea. So there's a tripolar pattern of sea surface temperature anomaly in the North Atlantic. And also the contour is contour is a sea surface temperature, mean sea surface temperature in the control simulation. So this is the ocean heat content anomaly. Global mean is removed. So you see the largest increase in ocean heat content is in this region of the shelf break, and also in the Gulf of Mexico and the Caribbean Sea. So the ocean heat increases faster than the global mean. So this is a critical region for the hurricane. And B, so that's the ocean mesoscale eddy activity. So the blue color means the CO2 tends to reduce the ocean eddy activity along the Gulf Stream. So these ocean change patterns are related to the Atlantic Meridional overturning circulation. So this is a schematic about this overturning. So in the upper ocean, the warm water flows northward. At the high latitudes, the warm water cools and sink into the deep ocean. And then the cold water flows southward at the deep ocean. So this is overturning, large scale. So if you integrate the transport across the Atlantic Ocean, so you can get an overturning stream function in the control simulation. So positive value means clockwise circulation. So you can see the warm water flows northward in the upper ocean. So at the high latitudes, so this water sinks into the deep ocean, and at the deep ocean, the water flows southward. So this is the overturning in the Atlantic Ocean. And in the control simulation, this overturning circulation show interannual to multi-decadal variability. So this is the black curve in this plot. But in response to CO2 forcing, in the 1% CO2, you can see this overturning circulation weakens. You can see the strength of the overturning actually declines. So this weakening of the overturning actually is responsible for this dynamic sea level change pattern, and also the SST, the pattern in the North Atlantic. Okay, so now let's look at the storm change, the atmospheric side. So in response to the CO2, 1% CO2, both the tropical cyclone and the extratropical cyclone become stronger. So this is because the ocean surface temperature increases. So warmer ocean surface can provide more energy to the storms. So storm gets stronger in the CO2 experiment. But the total number decreases, especially for the extratropical cyclone over the North Atlantic region. So A is the track density for tropical cyclone. So the contour is the control run. The shading is the anomaly in the CO2 experiment. So high value means high tropical cyclone activity. So blue color indicates the tropical cyclone activity reduces. So you can see the warming actually reduce number of the cyclones. This is a C plot, the total number of tropical cyclone as function of time. So you can see by the end of the model in simulation in the CO2 experiments, so the total number slightly decreases. But for the extratropical cyclone, so the decrease is more significant over the North Atlantic, that region. So this is a time series of the storm over the North Atlantic. So you can see the difference between these two curves. So and also the dark blue here so indicates the reduction of the extratropical cyclone. So this reduction of the number is related to the SST anomaly pattern here. So the faster ocean warming north of a Gulf Stream actually can reduce the temperature contrast across the Gulf Stream here. So therefore, it can reduce the baroclinicity in this region. So therefore, that can reduce the total number of the extratropical cyclone. Okay, so extreme sea level. So this is a daily sea level anomaly distribution. So this is the histogram of the daily sea level anomaly. So in the control simulations, that's the shading, gray shading here. And also the blue color is the distribution in the 1% CO2 simulation. So the red is a stronger experiment, above 4 times CO2. So the upper panel shows the so the horizontal axis is the daily sea level anomaly in meter. So the vertical axis is the total days over the entire northeast coast, over the entire southeast coast, over the entire Gulf Coast. So basically, you can see this is the probability density function, PDF, of the daily sea level anomaly. So the takeaway here is that the increase in external forcing progressively shifts the PDF to the right and towards the higher surge values. So you can see the shift to the right in all 3 coastal regions. And for the northeast coast and southeast coast, for these 2 coastal regions, so the shift is mainly due to the regional dynamic sea level rise and the global steric sea level rise. But for the Gulf Coast, the elevated storm surge is mainly due to the change in storm characteristics. Remember, the storm gets stronger, right? So, and also due to the global steric sea level rise. So you can see the longer tail of the PDF in the CO2 experiment. So these 3 panels are the control 1% CO2 and the abrupt 4 times CO2. So the right 3 panels are the historical simulation and the future projections. But you get the similar conclusion. So the increase of external forcing progressively shift the PDF towards the higher surge values. So this is a time series at 3 coastal cities. So this is the daily sea level at New York City. So blue color is the control simulation, and the red color is the CO2 simulation. So you can see the upward trend in the CO2 simulation. And this is Miami. So this is New Orleans. So the horizontal lines are the return levels. So you can see the anthropogenic signal can emerge as early as in 20 years in the CO2 experiment for the 1 in 1 year event. So that's the triangle show the time of emergence. But the emergence of anthropogenic signal is delayed for the higher surge event, the 1 in 100 year event. So you can see it's delayed. Miami, so the emergence is early because the sea level fluctuations is small, so it's easy for the anthropogenic signal to emerge. But at New Orleans, you can see the emergence is significantly delayed because the very large fluctuation, sea level fluctuation due to the landfalling hurricane. So the time is much later. Emergence time is much later at New Orleans. Okay, now before get to the conclusion, and the caveat and the conclusion, I want to show you the animation. So the left panel is the contour simulation. So these contours are the storms. This black contour are storms, and the shading is the daily sea level. So red color means higher surge event. Blue color is a negative surge event. So you see the right panel is the CO2 experiment. So you can already see the sea level rise, right? So sea level is higher, but the storm surge also higher in the CO2 experiment. Let me show you the animation. So this storm approaches the Gulf Coast. So you see the surge height, extreme sea level is higher in the CO2 experiment, right? So because the storm is stronger and the sea level rise. Okay, so I want to repeat the caveat for this study. So the model does not include ice sheet model. So the land ice, that part is not included and does not simulate tides. So there's no tide surge interaction and also no strongest storm, category 4, 5 hurricanes, not simulated. And also use the daily surge, daily data rather than the hourly data. There's no subsidence, land subsidence. Okay, lastly, the conclusions. So this is the first study that used a fully coupled global weather climate model system to investigate extreme sea level under climate change. And even without climate change, the Gulf Coast is the most vulnerable to storm surge, particularly at New Orleans. And in response to greenhouse gas forcing in the CO2 experiment, so the elevated storm surge along the East Coast is mainly due to the background sea level rise. And also along the Gulf Coast, storm surge is sensitive to the modification of hurricane characteristics under the greenhouse gas forcing. Okay, so I'm running out of time, so I just stop here, and maybe we still have time for questions.
All right. Thanks for that, Jianjun. We have time for a couple questions. Joellen, please.
That's amazing, Jianjun. I had no idea that CM4 was so excellent. Wow. I've really just never seen anything like it. I'm stunned. But what are you going to do about the no 4s and 5s? Do they need to go to even higher res? How do you deal with the fact that the Cat 4s and 5s aren't there?
Yeah, that's a good question. So we did some comparison between the standard version of CM4 and the CM4 high res. So there is the results are qualitatively similar. So, but the magnitude is different. So the magnitude is higher in the CM4 high res. So that gives us some confidence. So the result from the standard CM4 can provide some new information. But I agree that eventually we need to go to higher resolution, like 1/4 resolution for the atmosphere. That probably can resolve the Cat 4, Cat 5 hurricane, right? So if that model is available, so we can take a look at the storm surge again to see how the result looks like.
Wonderful, wonderful. Is NOAA moving in this direction? Sorry, I don't mean to take somebody else's spot, but the follow-up here is, how's the Weather Service handling this? I know that they've transferred FE3, which is the atmosphere of CM4, to the Weather Service, and they're using it. And I know they want to do better storm surge products. What are they thinking?
I think they use the system they are using are decoupled. So they run they run the weather model and they force the storm surge model with the result from the weather model.
I heard that.
Yeah, decoupled, but this study is fully coupled. Everything is put together closely.
I heard they're thinking about coupling the ocean as HICOM instead of MOM6. I think that's weird, but
okay.
This is awesome. That's I'll stop and let other people ask, but woo! Hair blown back.
Any other questions for Jianjun? You can type in the chat or raise your hands on the participants list. Jianjun, I have a quick question. In one of the plots that you had that showed the skewness, there appeared to be extremely high positive skewness in sort of the abyssal Gulf of Mexico, in the central part of the Gulf of Mexico. I'm trying to understand where that signal might come from. What are the dynamics for the non-coastal open ocean skewness?
I think that's a good question. Actually, that's due to the eddy.
Loop, so that's what I thought, that it's probably loop current eddies that are piling up.
Yeah, because in the Gulf of Mexico, the eddy is anticyclonic. So you have a higher sea level, right? It's a warm core eddy. There's basically no cold core eddy. So you always have a warm core eddy. So warm core eddy give you the higher sea surface height.
So then would your prediction be that in a warmer world that you would see more eddy shedding from the loop current?
So the model actually simulates a decrease of eddy activity in the Gulf of Mexico in the CO2 experiment.
Right, and that's consistent with some of the earlier work as well. But I'm wondering then, why does that give rise to that positive skewness then?
So that positive skewness is for the control simulation.
Got it. Yeah, thank you. Yeah, very interesting. Other questions? Maybe time for one more quick question if anyone has it. Okay, Jianjun, thank you very much. And then we're gonna basically take a short break and then start the class led by Marcus and Paul Kapp to discuss more in detail about today's talk. So thank you, Jianjun.
Thank you.